Hey everybody, thanks for your patience. Sorry for the technical difficulties. We should be ready to go, so if you can take your seats. You can wind down your conversations and
completely in line.
It's our last full talk of the day. We're a little bit over time, but not too bad. We'll have 2 more half talks after this, but if you can, give Nicholas your attention.
Hello, is this on?
Yep, you're on.
It's on? Good. All right.
Go ahead.
Right. All right. So, good afternoon. So I'm presenting on DCompute, native and convenient heterogeneous computing for D. All right. Before we want to start, I just want to conduct a small survey. So can you put your hands up if you were there or watched John Colvin's presentation from last year? That's 30% or 40% or something? All right. And put your hands up if you've used OpenCL and or CUDA. Significantly less. All right. So this talk will cover what I've done to LDC to get for this the libraries that I'm in the process of writing and using DCompute and some future directions. I'm going to start with the state of hardware in D. All right. So in terms of the hardware that's accessible for you to program in D, all of the major compilers support x86, which is good, because most of these things, I'm assuming, are going to be x86. GDC and LDC have support for ARM. I don't know about the rest of the other targets. In theory, LDC also supports MIPS and PowerPC. I'm not sure how well that's targeted. But so far, so CPUs. What about other kinds of devices? Whoops, that good. Yeah. So in the world of heterogeneous computing, there's all sorts of weird and wacky, wonderful hardware, some of which is nice to program and some of which are not. You got DSPs, FPGAs, and GPUs. So if you want to program these things traditionally, DSPs, you'd use C, because that's everywhere. You can also use OpenCL. FPGAs use hardware description languages, Verilog, VHDL, and now DHDL. You can also use OpenCL for them. They have implementations for that. And GPUs, there's sort of 2 workflows for that. There's the sort of graphics and the compute. For graphics, you write shaders in either GLSL or HLSL. And for compute, you've got either OpenCL or CUDA. Now, it should be obvious from this that OpenCL is everywhere, and therefore, if you want to do heterogeneous computing, we're going to want to target OpenCL. However, CUDA is very dominant for compute, so if we can, we want to target that as well. I'll come back to the graphics stuff at the end, but most of this talk is going to focus on the compute side. All right, so quick recap. CUDA is NVIDIA's solution for GPU acceleration. You write it generally in CUDA, C++, or Fortran if you're really adventurous. What you get from compiling that is you get PTX, which is kind of like a target-independent assembly language for their GPUs, and that gets compiled into SAS, which is like a black box binary format. It's generally well integrated and reasonably nice to use from C++. OpenCL's got a lot more targets, and the recent versions have sort of standardized on SPIR-V as their binary format. The kernel languages are okay, I mean, as much as they can be. It's not a very fun domain to be in. Well, depends on what you think. But the APIs to use and call them are horrible, to put it nicely. Yeah, those of you who've used it will know what I'm talking about. So, CUDA has vendor lock-in, and OpenCL isn't very nice to use. But LLVM supports SPIR-V and PTX, and LLC supports, LLC's backend is LLVM. So, and to DCompute. So it's a set of sort of 3 things. There's compiler extensions and changes to enable writing kernels in D. There's the library portion, which is using D's metaprogramming to automate calling of the kernels, because that's the most painful part. And then we can, once we've done that, sort of set up a set of pre-written kernels for standard use to increase adoption. Yeah. So the compiler work is mostly done, as in it's functional. There's a couple of things that don't yet support. Pipes and images are sort of magic types that I haven't yet done. Global variables, because you need to, you need to put them in an address space, so because with GPUs you've got different portions of memory and you've got different pointers for each of the different portions of memory, which is a giant pain in the neck, but that's the way it is. And also, better errors and error reporting would probably help a bit, because it's not very, they're not very readable. And some SPIR-V optimizations would be nice, because SPIR-V is the format that gets induced and then re-optimized by the thing that's consuming it. But it would make debugging a SPIR-V a lot easier if you don't have a whole lot of common sub-expressions and whatnot in there. So the way that LLVM targets CUDA and OpenCL is mostly tacking bits of metadata onto the modules. There's also different calling conventions, which is relatively easier to do. There's address spaces of pointers, so unlike normal D, you've just got a pointer and it points to somewhere in memory. Because you've got different portions of memory, you've got a different type of pointer for each one of those, and then you've got a general one that can point anywhere. There's a bunch of special types, so images, pipes, and then there's a bunch of intrinsics kind of thing. So for getting what index am I when I'm doing when I'm trying to get data from memory. The intrinsics is in quotes because OpenCL's ones are currently sort of magic, by which I mean instead of being normal LLVM intrinsics, they're mangled as like C++ Titanium with some weird extensions for, I don't know why. So now that we can target OpenCL and CUDA, we need to decide on a compilation process. We could do it like OpenCL, where they have complete separate compilation, but that loses all of the compile time information, which is something that we want to keep. SYCL, which is the single source OpenCL, is kind of like a hybrid where you have like your kernels are lambdas. And that hides a lot of runtime magic, which we want to do in the library because we can, and that's a lot more simple to do in the library. CUDA has sort of hybrid sources as well, but different to SYCL. That also has the same problem with runtime magic, and it also makes semantic validation a lot more difficult when you've got kernel code and host code in the same file. But what we want is something that fits well with modules and retains all of the compile time information that we can. So, well, it's actually up. It shows up reasonably well. All right, so targeting these DCompute is hidden behind that compile switch. You just give it a list of what target it is you want, followed by the version number. So the way we go about determining what's for host code and what's for device code is we have a bunch of magic attributes, which I hope are fairly self-explanatory. We can compile normally for the host with no module, with no attribute. We can compile it for both the host and device for shared code implementations, and then kernels and other device-specific code for devices only. So what it looks like when you're doing that is you've got an @kernel, which is in LDC's magic attribute module, which the compiler picks up and generates code for that as an entry point, as a target entry point for the GPU. And you've got a bunch of, that's the pointer type there. You can see global pointer is a pointer to global memory. There's a bunch of other ones as well. That if DCompute reflect is an ugly hack that I wish I didn't have to have, but it or something like it is required, because for D, when we're targeting different things, we have static if and like for the front end that produces conditional AST effectively. That's kind of like a Codegen time if, so that you don't end up generating intrinsics for things that you don't have. It'd be nice to not have it that ugly, but yeah, unfortunately that's just the way it is, and because we need that information to determine whether we should call an intrinsic for CUDA or an intrinsic for OpenCL or whatever. And there's a bunch of ABI stuff, and I said the metadata before. Wait, where'd that go? And that Codegen time if is literally just check if the conditions to the statement match, and if so, call it. Otherwise, just omit the else or the if branch or whatever. So doing the compilation in this manner has a number of advantages. It's done in one compilation. There's no need to worry about multiple invocations of the compiler. Secondly, templates. I don't really have a working understanding of the D symbol table, but from what I understand, templates behave weirdly because they end up where you instantiate them, not where they're defined. And so to get around that, I force effectively what's under LDC's single object switch, which is just put them all in one. So effectively you do the same as emitting one object file. And the biggest benefit is we retain all of the compile time information on the kernels. So, where did that go? Yeah, so that enables it for use in the runtime libraries. So there's sort of several sections to the runtime libraries. There's a standard library for compute operations which expose all of the intrinsics for the GPUs and whatnot. That's used with kernels. There's a driver which handles the differences in the runtime APIs, handles all the host device interaction, launching kernels and managing memory. And then I want to get around to eventually doing a sort of standard collection of kernels so you can, without sort of a whole lot of knowledge, just do some offload some computation-intensive tasks to GPUs if they're available. It's sort of like, think of it sort of like thrust. So the standard library for DCompute contains a bunch of things. Indexation, so you know which item you are. There's some synchronization primitives. There's vectors, there's SIMD and geometric. There's the usual host of math stuff. There's some image stuff, but images don't yet work. There's sort of packing functions and whatnot, atomics. And then there's sort of group operations as well. These are backed by libdevice and PTX, LLVM PTX intrinsic, and for OpenCL the intrinsic magic stuff at the moment because of the mangling thing right now. Let's figure out how to do this. That worked. All right. No, where's my mouse? Down. No, inverted scrolling. Wonderful. Standard. So index is the one of the few modules that I've actually completed, and we'll click on it and scroll down. So this is the let's focus. This is the attribute at the top of the module. What this and most of the other ones are going to look like is they're going to import the relevant portions of the OpenCL or CUDA sections. Where am I? There's just some notes on some naming conventions because OpenCL and CUDA use local to mean two completely different things. So I just got rid of it. And all of the stuff looks like like this. Most of the stuff I've got pragma inline true because this you want to be in the host, so the user's kernel code, not a library, because if you're trying to link two modules, it becomes a lot more complicated than it needs to be. I'll have everything as templates as well, so that it only gets instantiated when the user uses that to reduce, so that you only get what you pay for, basically, and also so that you don't end up with any symbols that end up in a different SPIR-V or PTX module when you build it. So you don't, when you build the runtime libraries, you won't generate any GPU-specific code. And this is just showcasing use of DCompute reflect. So if we're OpenCL, 0 is the wildcard. So any OpenCL version, just forward this to the intrinsic, and this it's all pretty much the same. You just do some, because CUDA does things differently, you need to multiply things to multiply by the offsets and strides and whatnot. Right. Oh, no, that's inverted scrolling. So if we go back to that and then go, come on, index. And all of the CUDA stuff looks like this. It all just forwards to the intrinsics, and inverted scrolling. And the OpenCL stuff is similar, except that it's got an XN C++ there because this was taken from stuff that was just originally supporting OpenCL C and C++. I haven't got around to changing that yet because it's slightly more difficult. And yeah, because it's Itanium, it won't work on Windows yet because that'll be mangled as something different to what, because the host, the front end will mangle it as Microsoft C++, and then the back end will be looking for Itanium. So that's in the works to be fixed. All right, let's go back to, how do I just go, what the hell? Hey, that worked. I don't know why it worked, but it worked. Right, next. That change? Why is mine, hang on. There we go. All right. So, the driver's still a work in progress. I'm working off what John Colvin did last year for with his CL wrap, but I've also got to implement that for CUDA as well. So the driver handles all of the API interactions, which are the stuff that you don't want to have to do by hand because it's all really tedious. And it's heavily redundant from the vantage point of D, because we only want to write boilerplate once, right? So the way we go about doing that is ideally we want something that looks like this, right? We've got a kernel, it returns void because all kernels return void. It's got a name, it's possibly a template, it has some parameters, whatever. And we want to get a configuration because we don't know what devices we have. We get a default device from that. Get the default device's queue. We have some data. We make a buffer out of it. And we enqueue the kernel, and we wait, and we read it back. So we can do the first sort of 4 lines and the last line in pretty much any language. But I think the fifth line, I hope I can count, whatever. I think it's pretty much only possible in D or with runtime reflection, but we get that at compile time. Because what we can do is we can decompose the, where is it? We can decompose the alias template parameter, which is the kernel to instantiate, which is the kernel to call with to its function type and mangle of, and then we can, by the code there, generate and reflect over the parameters of F, and then call CL kernel set arg and CU launch kernel, depending on what device the queue comes from. The syntax there with the the two sets of parentheses is because you want to separate the calling of the parameters you're using to enqueue the kernel. So generally what size of things, like how big is your X dimension, Y dimension, or Z dimension, or whatever, and then how you break that up. There's also what queue you want to enqueue that on, and there's also the size of local memory, I think is the fourth argument. But that's sort of modeled slightly after CUDA's kernel name triple angle brackets size and I think call it stream or something, which is effectively the queue, and then you give the arguments to the kernel, and that's translated. So yeah, we can generate and statically type check what arguments we're passing to the kernel, so that we don't get any runtime type errors or lack of type errors, and then just get silently crap results. So the things I want to do with the collection of kernels is show how to do things and how not to do things, because it's really, really easy to do things horribly, horribly wrong in when you, particularly if you're not familiar with writing code for GPUs. It'll also serve as a functional example and cover common use cases for things like convolutions, your Fourier transforms, reductions and whatnot. And also possibly pre-compilation, because this relies on LLVM's backends and therefore obviously only works with LDC. But so if we were to do pre-compilation, we could get this working with DMD and GDC, assuming that the mangling is all the same, which I think it is. Oh, I'm way too. Right. And so the things, future work is to make SPIR-V use intrinsics. I'm working on this at the moment. That's a lot more complicated than I hoped that would be, but such as it. Compiler tests are something that I want to do a lot more of, because that ensures the correctness of the code. But that's made somewhat difficult by the fact that you can't use, you can't necessarily do the unit tests properly, because for one thing, you can't assert in device code because the default behavior is to throw an error. I could possibly change that to just crash, but or forward to, I think there are like assert intrinsics that you can forward to as well, so I've got to get around to doing that. But yeah, getting a testing framework up and running would be good, because there's a sort of wide variety of hardware, and there's sort of different API vendor versions with some with bugs and some with different bugs, and I'm sure that those dealing with games know all the fun of drivers, and that applies here. So I also want to finish sort of working on integrating the rest of CL wrap, and then start on a CUDA version of that same functionality, sort of to provide a high-level API over that, so that you don't need to worry about calling the different functions that you don't care about. You just want to launch a kernel. You don't care that you need to set some particular parameter of the kernel. And then sort of external library integration, I think, would be a good thing to try and offer. So with things like MER with NDSlice, GLASS and CV and whatnot, but also all of the other scientific libraries that are in the ecosystem. And then also lowering the barrier to entry, I think, would enable like all of the algorithm gurus in the audience to try out new things if they don't have to write a whole lot of boilerplate in order to do so. And also provide those standard algorithms that are used for standard algorithms that are used on GPUs. So, yeah, in conclusion, DCompute is an extension of LDC to support running OpenCL and CUDA. all at the same time, because that way we retain the, the compile time information. One-time libraries are work in progress. Yeah, the demo was going to happen, but technical issues. And we're able to do this in D because we have awesome templates and introspection that work, and we can do all of that we can do all of that, the generation of the different things at compile time with library code rather than compiler code, because getting it right in compiler code is a lot more difficult. And yeah, sort of world domination of HPC is should be within grasp if we can get this, because there's a lot of craze right now with machine learning and whatnot. So I think the faster we can get this working, the sort of the bigger the market penetration we would get. Yeah, so I don't really have a whole lot of experience with CUDA. I've done some stuff with OpenCL, but I think one of the biggest challenges with this will be testing on lots of different hardware. So if you want help with this, come talk to me afterwards. Yeah. So I'd like to thank John Colvin for giving me the idea to do this stuff, and all of the compiler folks for LEC, David and Kai, who unfortunately aren't here, and a special thanks for Johan Englund helping me with all of my compiler problems. So you need a specific LLVM in order to get SPIR-V support. I'm in the process of trying to get it in mainline LLVM, and then that'll trickle down through the releases. So eventually, that'll be master. Also, with LDC, eventually, hopefully, that will get merged into master, and the runtime libraries are available at the last link. So, any questions?
So you're talking about having sort of standard kernels. One of the interesting things that you can do if you have little bits of standard stuff, like you're talking about sort of reductions, convolutions, that sort of stuff. If you can find a way to compose them, that's when it gets really interesting from a user perspective who doesn't want to become an expert in using GPUs, but they just want to go, like we have with ranges, you go like map, filter, and so on, or you think like the ND slice or MER APIs, there's lots of this composability of things. And if you can get it so that you don't have to do round trips to the GPU and back between them, so you can just plug them into each other, that'd be very interesting. I think you can probably do that, and that would be really, that's a huge game changer if you can do that, because currently you have the choice with almost all the libraries people use that you can go, oh, I'll call a GPU library and get a result. And then you go, okay, now I'll call the GPU library again and get it for the next stage.
Yeah. So you'd be able to do that by writing functions just directly, which is not particularly composable, but I think the best you'd be able to do is sort of, because that works with the lambdas, so you can, where you've got the alias symbol for the template, you can just insert a lambda and that'll work as well, because unlike C++, we generate names for lambdas, which is useful when you're trying to do that kind of stuff, because that was part of the hacks for Sickle and the like, is that they don't have, the lambda symbols don't have names, so you can't refer to them. But you should be able to sort of get a lambda, and in the lambda do a bunch of compositions all in one go. But yeah, you'd probably have to have some hackery with what arguments you give the kernel to begin with. So that should be doable, but I just need to sort of spend a bit more time thinking about it, and that's got to wait till after the library integration of the runtime library support. Any more?
Yeah. Well, first the conclusion that the world domination is within graphs is very exciting.
Yes.
I hope it happens soon.
So do I.
Yeah, and I could see that this is still in early stage, so do you see that some real world example will happen at some point? Like
Well, you can build the kernels with D at the moment, and you should be able to insert that into, if you've got a pipeline already set up to do heterogeneous computing, you should be able to just insert that there. But I think the real advantage will become, because you get wins from doing that as well, because we have sane templates unlike C++, and C doesn't have them at all, and you've got all the static introspection, so there's a win there already. But I think particularly with OpenCL being able to call it nicely in sort of like on the fifth line there, and not have to do like a whole bunch of function calls and then a whole bunch of function calls within a loop to set all of the arguments, and then for like 50 or like 30 lines of boilerplate to call one kernel. Well, it's dependent on the number of arguments you've got as well. But we should be able to also support, have a similar level of ease of use of CUDA. So.
So I think the first next step would be to have the LDC support for this officially in the master, right?
Yes, I wonder that I'm getting around to doing that.
First, I'd like to thank you for the awesome work you're doing to get this GPU support. My question is, what are the main differences between device and host code? What are the D features that you can't use in device code? Is there some hardware-specific limitations?
Yeah. No function pointers, no dynamic call graphs, so that therefore no exceptions, and no asserts as well. We're going to hope to change that. I've got a list of them somewhere, I think. But there's what else can you not do? You can't access host-only visible symbols. Like if you got a module that's compute only and a module that, and you import, if you cross import and then try and write to a global variable, that's not allowed. And stuff that when you've got a physical separation of the system, you can't just magically cross like that.
How far away from being able to use std range and std algorithm on GPUs?
But all of the template only stuff should work, although I'm not entirely sure how these symbol tables work with respect to templates, but I think it works because when you get the AST, it's referenced, so you have the module, and that's got a list of top-level references that are things, so it's got all the things that are declared directly in that. It's got all the stuff you import from object.d, and then it's got also the list of references to all of the templates that are instantiated from that module. So if you reference standard algorithm and stuff from that, assuming that it's compliant, assuming that it doesn't do anything you're not allowed to do in kernel code, then it should just work. I think it was Johan as well.
Is there one last question in the front?
Have you thought a little bit already about how to integrate this in LDC? And specifically, would it make sense to pull in your changes to the compiler separate from the runtime code?
What do you mean separate? Oh, from the runtime.
Okay, the reason I ask is maybe I think that the compiler changes that you're making to LDC itself this is kind of settling, and you don't make so many changes anymore. And,
well, I've just been stupidly busy this semester, but.
Okay, but anyway, the work is now in the runtime library, right? That's where a lot of
most of the work, yeah.
Yeah, and I wonder if you want to split this, like merge your stuff into LDC
Yeah.
And then keep the runtime library in a separate Git repository just to have...
It's already in a separate Git repository. The runtime stuff is in the stuff that I just showed there. Unless you meant the stuff for D-runtime, which that still needs to be in the magic stuff.
Exactly, but that's fairly limited at the moment, I think.
Yeah, that's like a couple of symbols in LDC attributes, and then a couple of symbols in the DCompute types or whatever it is. But those can go in separately. Oh, obviously the runtime, the LDC stuff needs the D-runtime symbols. But the D-runtime symbols can go in before that, because that reduces merge conflicts by a whole lot. Any more?
Unfortunately, that's all the time we have for questions. Thank you, Nicholas.
Well, thank you.
Take a quick 5-minute break, and then we'll come back for our second to last talk with Kai.